Okay, so this is homework number 3 for problem number 3-24 right here. We were asked to find the rate of heat transfer as well as the rate of the temperature of the glass. To begin, we drew this resistance right here for the system that we have with 2 convections and 1 condensing resistance. We calculated the resistance to find an R total. That R total can then be used right here in this heat transfer equation for the T infinity 1 minus T infinity 2 over your R total is equal to 707 watts. And then using this for the convection on the outside, you can find the temperature on the inside being 4.4 degrees C. For question 3-73, we were asked to find the thermal resistance of the wall as well as the heat transfer. To find the thermal resistance of this wall with 2 pieces of concrete on the side as well as a parallel glass wood resistance, we summed all the resistances, or we solved for all the resistances over here, got them with degrees C per watts as the units, and then we to calculate the parallel resistance, we used 1 over R total is equal to 1 over R glass plus 1 over R wood, and we found that R total for the parallel, and then used the R combined to find the parallel to get a R total. Once we found our R total, that was part 1 of the question, we can then use this Q equation down here to solve for the total heat transfer. In question 3-94, we had this long wire right here, and we were asked to find the heat transfer of the water as well as the velocity with a 3 degrees temperature drop. First of all, to find the Q of the water, once again, we use the resistances found between the piece of pipe, which can be seen here, as well as the resistances over here. We calculated the resistances to get an R total. We had to as well calculate the radiation heat transfer coefficient to calculate the radiation resistance, as well as some convection going on from the fluid motion inside of the pipe. We then used our H's and all of our R's to get an R total, which could then be solved for a Q. Once the Q has been solved for, we can then use Q equaling mCp delta T to solve for an m dot, and using that m dot we can use rho v AC. Knowing our rho and our AC and our m dot, we can solve for the B. Lastly, for question 14-57 right here, we were given some concentrations of hydrogen in air, and we were asked to find the mass transfer from diffusion for hydrogen with some thickness of the membrane between the hydrogen and the air. We used the NDiff equaling the diffusion coefficient times the concentration of hydrogen and the concentration of water over the thickness of the membrane to calculate the NDiff, which then can be converted to a mass diffusion coefficient by multiplying by the molecular weight. This was then repeated for the other thickness down here at the bottom, 4.55 millimeter membrane.